Okay, does anyone want to tell me why does the reverse rate get faster as time goes on? Yes, Marilyn, once you finished your bite. Yeah, we started out with none and we're making products, so obviously the concentration is increasing. If the concentration increases, what do we get more of? Collisions. And if we have more collisions, then the rate is faster. Do we need to go over why the forward rate slows down, or are we okay? We're okay? All right, moving on. So we get to a point where they are no longer changing. Both rates have equaled out. So those two rates are always going to meet somewhere in the middle. Okay? I always just put them in the middle because we're only in grade 12 and I don't think it matters exactly where you sort them out at this level. Okay, so you know, if you wanted to meet 3/4 of the way up and 3/4 of the way down, whatever, as long as they meet. All right, what does it mean that it is a dynamic equilibrium? Tell your partner, what does it mean that the equilibrium is dynamic? So perhaps it would be helpful to know that static means unchanging and dynamic means changing. Yes? What is changing in the equilibrium? What is changing in that system? Pardon me? It's not the rate, because the rate is staying the same. Yeah, the forward and reverse reactions are still occurring. Molecules of reactant are turning into molecules of product. Molecules of product are changing into molecules of reactant, but the overall concentration stays the same. So it's important, if you're defining dynamic equilibrium, that you include that dynamic portion, that the forward and reverse rates continue to occur. Okay, so the reaction has not stopped. Forward and reverse rates have to keep going. Blah, 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 blah. We talked about the word macroscopic last day. What does macroscopic mean? Observable, visible with the naked eye, something you can just look at and see. What is the opposite in this context of macroscopic? Microscopic, or more accurately than microscopic, would be at the particle level. So if you could see the particles, you'd actually see, ooh, turning into reactant, turning into product. Ah! Okay. They might not make that sound. Okay. So all the macroscopic properties are constant. So what did we say? Number one, what was number one? I don't even know, it doesn't matter. Oh, one, the reaction is not stopped. Two, forward and reverse take place. Oh my God, I wrote a lot. So here are some examples of macroscopic properties. Concentrations, that's probably pretty obvious. If you've got a gas, the total pressure is going to remain the same. Obviously, as we saw last day, once we had reached equilibrium, the color, if we have a colored species, is going to remain the same. If we are at equilibrium, the temperature is not changing, density, pH, all of those are things we can observe with the naked eye, or just like some easy tools. There's a pH meter you can use, density, you can measure the mass and the volume, and you should be good. If no changes are made to the conditions and nothing is added or taken away, a system at equilibrium will remain that way forever. 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 Okay? However, that's no fun, so we spend a lot of time looking at changing the conditions of an equilibrium. So, if you are defining dynamic equilibrium, you need to have two things. One, the macroscopic properties are constant, but particles changes continue to occur at the microscopic level. Or you could say the reversible system in which the reverse and forward rates continue at constant and equal rates. Either of those would be a good definition. I shouldn't have written that. Yes? Okay. Here are a few other things to consider. Changing the temperature will change the rates. We talked about that last day, yes? Now, it turns out, and we'll talk about this in more detail later, increasing temperature increases the rate of the endothermic reaction more. It also turns out that decreasing temperature changes the rate of the endothermic reaction more. The endothermic reaction rate is always affected more, whether you're increasing the temperature or whether you are decreasing the temperature. We can look at some kinetic energy diagrams and potential energy diagrams to prove that to you in a little bit, but for now, just take it at face value, okay? So, if we change the temperature, we are changing the rates in an unequal fashion, so you will no longer be at equilibrium. If you put something in or you take something out, you are no longer in equilibrium. And I don't know why they always say this. It's part of the thing. You can approach an equilibrium either from the left, if you just put in products, or you can approach it from the right if you just put in reactants. Either way is fine, okay? This is really boring. Sorry, this is just going backwards. What if we had started with all NO2 instead of, what if we had started with all this and none of this? The reverse rate would start out, yes, sorry, Casey. Bingo. Yes, both, it'll increase one more and it'll decrease one more. Yeah, it affects it more. Endothermic. What would the reverse rate be if we started with all NO2 at the beginning? It would be fast. And the forward rate out would start out at 0. As the reaction proceeds, the forward rate would increase, and the reverse rate would decrease. Eventually, the two rates would become equal, and an equilibrium would be established. Okay. Sorry, yes. You can totally switch them around. If you're given one, like if you're given a reaction, go with what's given to you, like as reactants and products. Don't just flip it on purpose. Yeah? But if you don't know, you can write whichever one wherever you want to. Yeah. Blah, 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 blah. To summarize, here are 6 characteristics of a system at dynamic equilibrium. The rate of the forward equals the rate of reverse. We've heard that all a million times, yes? Microscopic processes are occurring. They continue in a balance that yields no macroscopic changes. Did we know that? Yes. Did we know the system must be closed? Did we know the temperature must be constant? And uniform, yes. Uniform means the same throughout. Constant means unchanging. So it means you don't have like one area that's constant at 20 degrees and another area that's constant at 25, right? It's all like 22 or whatever. Yeah? Uniform means the same throughout. Constant just means unchanging. Equilibrium can be approached from the left and from the right. And duh, you have to have both reactants and products present for a system to be at equilibrium. How would you have an equilibrium if you didn't have reactants or products? Okay, excellent. Some exercises on that. Moving on to 2.2. Are we moving too slow, too fast? How are we feeling? Good so far? Okay. Tell me if I'm moving too slow or too fast. I can either pick up the pace or slow down, whatever you like. Color is an example of a what kind of property? Macroscopic. Technically, maybe we would do this like the next day, so you would remind yourself, but that's okay. We're reminding ourselves right now. And what kind of property? Observable. And don't forget my abbreviation for equilibrium is EQ with the little m at the top. At equilibrium, macroscopic properties are constant. At equilibrium, what is equal? Forward rate is equal to the reverse rate. Have I mentioned the word stress yet? I don't think so, right? Okay. A system will remain at equilibrium until it is stressed. This is a new word. A stress is a change that we make to the conditions. So you remember last day, who put the tube into the hot water? That was me. Yes, I stressed the system. So it's something that we do. Now, in these tubes, these tubes are glass tubes. There's no real way to get anything other than heat into or out of this system, yes? But can you imagine if we had a different piece of glassware that maybe had like a little valve coming out the side, and we could turn it on and we could turn it off? And maybe attached to that, I could have a cylinder of some other gas, and so I could like pump extra NO2 into here. So I could change the concentration of NO2 by pumping extra NO2 into here. Yes? That would be a change in the condition. Yes? Still a closed system, but that would be a change in the condition. Stresses, regardless of what kind they are, make the forward and reverse rates unequal. Where did I put my glove? So stress makes forward and reverse rates unequal. Stresses are considered to be instantaneous. They're not actually instantaneous, but when we are graphing them, we're going to say that that stress takes no time at all. Okay, so they will appear, let's see if we've got a concentration graph. So on a concentration graph, concentration versus time, And then if I've got a rate graph, that would be rate versus time. And let's look at a system where we maybe have some NO2 and we have some N2O4. Because those lines are straight and flat, what does that tell us about the concentrations? They are unchanging, yes? And if they are unchanging, what can you say about the system? It is at equilibrium, okay? So here we are at equilibrium. That was supposed to be like a cute little bracket. It was really, did not turn out well. Cute little bracket, there we go. That looks much better, okay. Now I might stress the system just like I talked about. I might inject, I'm gonna inject some N2O4 because it's less awkward, because I've not given myself much room on the NO2. That would be a stress. And do you see how it's vertical? That means it's taking no time. This would be right here. I inject some N2O4 into the system. You don't have to worry about how we do that, okay? You can imagine there's a little valve or whatever. It doesn't really matter. Somehow or other, I managed to get some extra NO2 into the system. This right here is the stress, and it is instantaneous. It takes no time, so that's why it's vertical. Yes? How did I put it in? I mean, honestly, it's going to take me, anything I do will actually take a finite amount of time, yes? However, for the purposes of graphing it, we're going to say that I can just do it like, okay? So we're just gonna be like, boom, it just goes up right in that one instant, okay? Now, if we had rates, what would my rates look like if I were at equilibrium? If I have my forward rate, they would be on the same line, and my reverse rate. And if you don't have two different colored pens, my favorite thing is to make one a dashed line and one a solid line, yes? So our forward rate would equal our reverse rate. I actually remember there was a student in my AP class one year, discovered that he was colorblind because he could not tell the difference between the red and the green line. Yeah, he did not know up till that point that he was colorblind. He's like, those look the same. And I'm like, have you ever had your eyes tested for color blindness? So he found out that he was colorblind. I do not know. He went for like, 16, 17 years of his life not knowing that he was colorblind. It was astonishing. Well, the thing is, he wouldn't know. Like, how would you know? I feel like other people should have noticed at some point. Or maybe he should have been like, why does everyone say that Santa Claus wears red and the tree is green? Why do they have two different names for the same color? Like, I don't know, but like, it's just, anyway, I don't know, but there we are. So if this was our reaction, and I added extra N2O4, which rate would I have changed? Would I have changed the forward rate or the reverse rate? I would have changed the forward rate, yes. Okay, so the forward rate would go up, and that would be due to the stress. And because it is due to the stress, it is going to be instantaneous, and it's going to be vertical. Like I said, that's not in real life, but that's okay. We can do anything on paper that we want to. So what kinds of things can be stresses? We talked about concentration, we talked about temperature, and the other thing that can be a stress is if you have a system containing gases, you can also change the entire volume of the system, which will therefore in turn affect the pressure. If I squish a container, if I make the container smaller, what happens to pressure? Increases. And if I make the container bigger, the pressure decreases. Okay? So 3 things that are stresses: concentration, volume, if the system has gases, which means also pressure, and temperature. So only 3 things. Things that are not stresses: catalyst, a change in surface area, and adding an inert gas. What does the word inert mean? Unreactive. Oh, I wrote that down here. Unreactive. What does a catalyst do to a reaction? It speeds it up. How does it speed it up? It lowers the activation energy. It lowers the activation energy by the same amount for the forward and the reverse reaction. So it actually speeds up the forward and reverse reaction equally. Yes? It changes the overall pressure, but it doesn't change the partial pressures of each of the reactant gases. So it doesn't change the amount of collision between the reactant gases. Yeah, you still have the same. If you think about it like gas concentration, the concentrations of them haven't changed. If you squish a container, all of the partial pressures get higher, all the concentrations get higher. Yeah? So a catalyst doesn't, because it affects both rates equally. If you change the surface area, it also speeds up both rates equally. And if you're having trouble imagining that, let's imagine that we have a beaker here. And at the bottom of the beaker, I have a pile of solid. Yes? Let's say this is AgCl, solid. AgCl can dissolve and form Ag plus and Cl minus, yes? But because this is a low solubility salt, this is also going to redeposit onto the solid. So far, so good. And once we have a saturated solution, this process is in equilibrium, yes? For every particle that dissolves, another one recrystallizes. So far, so good? What if I make my pile, what if I gave you more silver chloride? There will be more dissolving, yes, because there's more places for it to dissolve. But there are also more places for it to recrystallize, yes? So when you increase surface area, you actually increase both rates equally. Yeah? I realize I'm not doing a fair thing when I write things over on the side, because you guys don't have that over on the side. You don't have that over on the side page room on your page. I trust you to work it out. Have you worked it out? Good. Now, when we add an inert gas, it doesn't change either rate, because you're not changing the concentrations of the reactant gases. I'm going to put a little star here and put more space for next year. Presuming I have time this summer, I'll go through and do these things. Okay, so this is just a place for you to practice listing 3 things which are stresses and 3 things which are not stresses. Can you do it? Go. Okay, so tell me, the 3 things that are stresses, they make the forward and reverse rates temporarily what? Unequal. And they can either do that by changing only one of the 2 rates, either the forward or the reverse rate. Okay, so can you think which of those factors would affect only one of the rates? Concentration. Because if we change the concentration of a reactant, that does not affect the reverse reaction. It only affects the forward reaction, at least temporarily. It affects both of them. Yeah, so a temperature increase will increase both rates. So it could change both rates, but by unequal amounts, or by different amounts. I'm not sure why I chose unequal, but that's okay. So the factors that do this are temperature and pressure, volume. Because if you increase the temperature, you're increasing the temperature of both reactants and products, right? It's all in one container. You cannot increase the temperature of one side. Sometimes people are like, oh, I just want to increase the temperature of the reactants. You cannot do that. It is all in one container, yes? All right. These 3 leave the forward and reverse rates equal. They can either leave both rates equal by increasing both rates equally. Which 2 factors increase both rates equally? Catalyst and surface area. Or they can do it by not changing either rate at all, and the factors that do this is the inert gas. A system that is stressed will shift in response to that stress until a new equilibrium is established. It shifts in order that the forward and reverse rates are equal once again. This shift, unlike the stress, takes place gradually over time. So whereas you see a spike, a vertical, for the stress, the shift is going to be like, whoa, whoa. Yeah? The shift is always going to be fast at first, and then it's going to slow down as time goes on and we approach the new equilibrium. So let's say we have, let's say this is a concentration graph, and I have my NO2, and I have my N2O4. And let's say I increased the concentration of the N2O4, and that was our stress. Remind me, what did that do to the forward rate? It increased it. So this one got bigger, whereas this one remained the same. Yes? If that's the case, if the forward rate is faster than the reverse rate, what is happening to the concentration of N2O4? It's going to decrease because we are using that faster than we are making it. So at this point, now we are going to have the shift. So this is going to go down until it reaches a new value. And I'll explain why it has to end above where it started later on. But the thing is that this right here is a curve, because it is the shift, and the shift takes place over time. I actually haven't done a very good job at drawing this curve. The curve should have an initially steep slope that becomes shallower and then flat. Steep, shallow, flat. What would happen with our concentration of NO2 if our forward rate is faster than our reverse rate? It's all good. Concentration of NO2 is going to increase. So it's going to go up. And you'll notice that once again, the curve is steep and then shallow and then flat. Yes? What does a steep curve mean when it comes to a changing concentration? If the curve is steep, it means that the concentration is changing really fast. If the curve is shallow, it means that the concentration is changing more slowly, and if it is flat, it means that the concentration is not changing and we've reached a new equilibrium. Yes? So you always want your shift to follow the steep, shallow, flat pattern. Yes? Okay, so here is a rate diagram, for example. Let us label the old equilibrium, the stress, and the new equilibrium. Do you guys think you could do that for that rate diagram? The old equilibrium, the stress, the shift, and the new equilibrium. Is that what approximately what yours looked like? Pretty much? Okay, good. Yes. Would the, oh yes, this is also part of the, this whole thing here is the shift, like this whole section, blah, in there. Yeah, it would just look tidier if I didn't circle the, you can actually see on the next page I've put it in, but I put a nice box there, you know, it looks prettier than when I draw it on my page, yes. Okay, so at the moment of the stress, what happens to the forward and reverse rates? What happens to the forward rate? At the moment of stress? It increases. What happens to the reverse rate? At the moment of stress? Does not change. Now, at the beginning of the shift, are the slopes steep or shallow? Steep. That means if the slopes are steep, the rates are changing quickly or fast. Are the slopes at the end steep or shallow? Shallow. And that means that at the end of the shift, the rates are changing slowly. Here is a concentration diagram. What was the stress in this system? Tell your partner, what was the stress in this system? What did we do to the system that stressed it? Anyone want to tell me what was the stress? Change in concentration of NO, not just a change, but specifically an increase in the concentration of NO. So there's our stress. And do we need to go through the steep, shallow nonsense? Or can we skip it? Skip it? Excellent, good. Moving along, blah, 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 blah. When a system is at equilibrium, the forward and reverse rates are equal. The concentrations are constant, but not the same or equal. A stress is signified by a vertical line or vertical spike. And a shift shows up as a curve. Now, one thing I want you to watch out for is students have a tendency to draw me S curves. No S curves. S curves are bad. Okay, S curves are not a happy thing. These are not good. No S curves. I want it to be steep at the beginning, shallow later. I don't want it to be shallow, steep, shallow. Okay? Blah, blah, blah. No S curves, more S, no S curves. Here's another place where students go wrong. They try to draw their graph and they don't use a ruler and they're not very good at drawing. Yes? I'm not very good at drawing, so I have a tendency to use a ruler. If you are good at making a flat line that does not go like this or like this, because those are not flat lines, then you would want to use a ruler when you draw a diagram to show the new concentration. When you're drawing it for yourself, I don't care, but when you're drawing it for me, I want to see that once we have reached our new equilibrium, that concentration is steady. It's not going up, it's not going down. Yeah? Okay. Those are just, you know, things that 25 years of teaching have shown me that happen all the time. Blah, 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 blah. Oh, we're on 2.2b. Are we ready to do a little bit? Oh, we're out of time. Okay. Let's see. There were some questions in yeah, let's leave it. We'll do this next day. Do any of these things have questions? You could do the questions on page 15. Homework, page 15. Oh, and you could also do page 20, 21, 22, 23. There we go. Okay. Yes, they are. first made it, right? So I don't know what reaction mixture they put in there. It can hardly help from being in equilibrium because it just spontaneously either the two molecules come together or they split apart. Oh, it means that I could have a system where I start with no product at all. Okay, so if I had a cube of ammonium chloride, a solid cube, and I wrapped it in like ceramic, so it's not able to move, right? Now I open it with a closed container. Now I can break down into NH3 and CO2 gas. And now we're going to get very warm. Yeah? So it's possible to have a system where you have both at the start or you have both at the start. Most systems are just inequal. Yeah. Yeah, because it was darker. Yeah. Temperature due to the particles. Let's increase the temperature due to the particles. The particles move faster, and if they're moving faster, what happens to the number of collisions? Increases. And what happens to the energy of those collisions? Increases. So the rate cannot be getting slower if you have more collisions and they're more energetic. So the rate is getting faster. Yes. What? Okay. Temperature. Temperature. Where's temperature? Stress, changing temperature. So what's going to happen is, oh, I don't like this. And like I said, it doesn't matter whether you put this in the reactants or the products, okay? So when we heated it, it got darker, which means that my heat term is over here. Okay? Okay. Yeah. So what's going to happen is when I increase the temperature, this rate is going to increase. And this rate is also going to increase, but not by as much. So I end up with more NO2 than I do N2O4. Now let's say I do the opposite. Let's say I decrease the temperature. Yes? So the forward rate will be, oh, I drew this on the wrong place. Oh my God, that's too confusing. I have to fix that. Okay. So this one would be more, there we go. And this one would be more, but not as much more. So if we decrease the temperature, this one is going to slow down a lot. This one is going to slow down, but not quite as much. So they both slow down.
But then because this one is still, I mean,
this one is faster than the reverse rate.
And that's why it gets more colorless, right?
Yes.
But then, as we learned, that is really highly unlikely to happen. That they're gonna still be being, for their initial concentration,
Same concentrations, yes.
Therefore, let's say if this one has less
Yeah.
concentration, this one has more, then wouldn't it get more, since we have more this at the initial, if we put it to the, let's say the same two samples with the same concentration, and if we put one in hot water
and it's the cold water,
and the change is same, like change in temperature is same, then wouldn't it get more colorless faster than getting darker because this is less?
Oh, I see what you're asking.
Yeah.
I also don't know. I don't know. Because it's gonna depend on the difference in the rate. Right? And I don't know what those are. Yeah. And we don't actually worry about that in grade 12 or in first year.
I just came up.
Yeah. No, it's a good question. I just don't know the answer to it. Like, so I don't know if the shift is going to be faster or slower. Okay? We don't really worry about how much time the shift takes. We just know that it takes some time. Yeah? Save that for your university professors, for people with more education than me. I might have known at one point, but anything past first year is like now over 25 years old. So I've forgotten. Like calculus, I used to know calculus. I could not differentiate or integrate anything anymore. Yeah.
How do you write the equation like this if there's
right there. Still goes right there. Because the reverse reaction is endothermic and the forward reaction is exothermic. Yes, so the heat term is always over here because this is absorbing heat and this is releasing. Yeah? Yeah. You ask good questions, Joshua. Some of them are so good, I don't know how to answer them. Yes, it's so true. It's so true. Yeah, see you Thursday. Bye. Homework. Oh my God, you're killing me here. Stop recording.